Okay, so far we learned how the very basics about how the muscles contraction mechanisms are generated by the sarcomere, actin, myosin filament, and its cross-bridge sliding mechanism, right? So next step is how we can formulate them. Now we briefly understand how muscle contracted and how those contraction can be formulated in a mathematical form so that we can implement that as our equations of motion for the human movement. That's what we are going to talk about here. So one of the popular model is a Hills model based on the experimental observation. So for the force generated by the muscle contraction for a single muscle fiber, muscle physiologists wondered how those Fs are formulated. What's going to be the function of F? Like, is the muscle force is a function of muscle length, or the muscle shortening velocity, or the time, whatever. So the one simple example about the experimental setup, it looks like this. So you have a muscle fiber extracted from the animal, and there is a motor neuron connected. And then basically your brain sends a nerve signals to the muscle contract. However, this is just simply electrical signal. So instead of having those are connected to the brain, you can actually generate through the function generator, stimulator. So you just provide the electrical signal mimicking the action potential. Okay. And those action potentials are sent to the muscle so that there are like electrical signals are spreading out the T tubules, and then T tubules triggers the calcium release, and calcium release will generate the binding site open, and so on. That the muscle fibers actually start to shortening, right? And those shortening lengths are measured to examine the length curve, length and force relationship, and this force generated will be measured by the force transducer here. So by applying the various activation signal, electrical signal, you can actually make a graph as a function of length, shortening length, and the applied forces. That's what we can get a relationship of examining how the muscle forces are related about the muscle length. Also, you can vary, like instead of adding a force transducer, you can actually apply the constant load, like putting the hanging mass on it. So in terms of mass, the magnitude of the load applied to the muscle, you can actually obtain the force length curve or the shortening distance and the loading curve, etc. So based on the experiment, suppose that you obtain the muscle force profile like this. So active means you apply the electrical signal to the muscle. Passive means there is no electrical signal to the muscle. You just physically apply the force like a spring extension. And the results are looks like this. So the active graph shows you have some increase in the beginning, and you have a maximum value here, and you decrease again, and you have a passive components from sort of exponential increase, and then later some kind of linear, proportional to the forces. So you actually do the curve fitting to make a model for that. For the active curve, you have this kind of formula could be used for the modeling. Passive, you have some exponential function to be used. That's how we ended up getting the modeling for the muscle. So there are possibly many different mechanical or mathematical formulations possible, because for this one, someone would formulate it as a parabolic curve, or someone might use some trigonometric function or the other nonlinear function. So there are many different mechanical formulation or mathematical formulations are possible, but they all still share common factors that I'm going to introduce later for the Hills model. And also, as we explore more, the models can be more complicated to match the real muscles behavior. Researchers are continuously study about the muscle characteristics, and there are new findings about we should add this component to better represent the muscle model. Okay, for that, there are three key components for the Hills model representing muscles force generating mechanism. The first one is a contractile element, CE. There is a parallel element, PE, and there's series element, SE. So typical mechanical, not mechanical, typical the schematics for the Hills model looks like this. There are contractile elements mostly contributed by what? actin myosin sarcomere contraction mechanism. And there are parallel component to that. Okay, that's parallel element. And there is a, as you could see here from the muscle anatomy, there are muscle at the end. There's a tendons attached to it. So there's connection between the muscle to the bone. That's why we call the series elements here. Okay, so there are force applied to that bone by shortenings, or maybe external load is applied to the body, so that actually had transferred the series element to the muscle. So again, the contractile elements are due to the real muscle activation mechanism, AP signals to the muscle, and then researchers found that those are a function of length and the velocity. That's what I'm going to explain later in the next slide. And also parallel element, the researchers found that that's due to biconnective tissues, like one we just saw, like a sarcoplasmic reticulum, or the other, there must be other connective tissues exist, and we can easily imagine that those are pretty much combinations for the viscoelastic, right? The damping components and the elastic components in it. For the series element, it's mostly due to the tendon, and then of course there should be viscose components, but the tendons, it's been known to be pretty much dominantly elastic components. So that's a series element, what we are going to model later. So muscle model, briefly, composed by the three components. One is active contractile element. There is a connective tissue. There's nothing to do with the contraction active components here, and there is also series element by tendon. There are three big concepts for the muscle force generation. Okay, let's examine more in detail about the contractile element. By the experiment, researchers found there are three main components contributing those force generation by active neural signal. One is definitely the level for the activation, how your brain send the activation level is from between the 0 to 1. And there are the forces are definitely the length relative and velocity relative. Okay, so that's from the observation. So the force length relationship was been found, and force velocity relationship found, and they are all by independently multiplied to define the force characteristics. And Fmax here is just a coefficient. Okay, suppose that you run the experiment and obtain the force length relationship, like a x-axis is the length and the y-axis is the force, and looks like this. So there are some maximum value exist. Around that, there are decrease of the force magnitude. If that's the experimental observation, how would you model that? Well, this looks like some parabolic function, or maybe the sinusoidal function, or the other nonlinear function. Okay, suppose that you run the experiment, and then at the maximum x-axis as a velocity, and then with respect to certain value, I mean, if you increase the velocity, the force decreases. It looks like this. Okay, so in that case, how would you model the force profile? Looks like maybe exponential decay, or maybe reciprocal function. So that's how the researchers could vary their mathematical formulation for the Hirsch model. But one of the typical example could be the parabolic approximation for the force length relationship. So again, those force length relationship shows this parabolic behavior because of the cross bridge availability. Okay, we know that once you have many cross bridge action, that will generate the stronger shortening and stronger forces, right? However, suppose that there are there are 100 cross bridges, but only 50% are acting due to the dependence due to the structure for the length. So actual amount of overlapped actin and myosin filament will be contributing the total force generation, right? So that actually contributes those parabolic force profile of the muscle length curve, and the other parameters are just modeling components. And force velocity curve as well, it depending on how much muscles are activated, how long it'll take to recruit those muscle to provide the fast shortening, and then that it's going to be here as a simple example for the reciprocal function. Okay, and Vmax and number 4 here could be replaced by the other numbers, are just simple fitting parameter, the modeling parameters. So again, so contractile elements are composed by multiplication of 3 components, which is activation, force length, and force velocity. And force length has a maximum value in the middle. Force velocity is keep decreasing as you increase the shortening velocity magnitude. Now let's examine what's going to be the parallel elements. And then we could imagine those are from the connective tissues. There should include something like elastic components and the damping components. So it's a kind of superposition of both contribution. So viscous elastic components are formulated by the spring effect, and then by experiment, researchers found that there are exponential stiffness in the beginning, and afterwards it turns out to be a linear. For the damping, pretty much well approximated by velocity proportional resistive forces. So for those experimental behavior for the spring effect, one may propose this kind of formula that within the range for the contraction, it will be exponential, but at certain range, like critical point, like spring has been changed from exponential to the linear, we can have a linear kind of formulation afterwards. So this is one simple example how we can formulate the parallel elements, and those are all modeling parameters about how we can formulate those parallel, the stiffness effect. Those are parallel, the parameters are actually set to make a continuous change between those regions. Like a slack, when the muscle is slack, there's no forces applied. Between the slack and the critical value, exponential, after critical turns out to be linear, and the parameters make it continuously vary. Okay, for the serial components, mostly by the tendon, and then researchers found that those are pretty much elastic and exponential in the beginning, similar to the parallel elements of spring components, and linear spring later on. So pretty much a similar formulation, except all the formulations are in terms of tendon length instead of muscle length. There's a typo here, sorry. So it's all about the tendon length related behavior, and the parameters make it continuous transition between those regions. And then most of the thing like this series elements are attached to the bone, right? And then bone is actually the point where the external load to the other connections or from the externals are applied. So sometimes we, instead of having a serial elements of modeling, we just directly assume those external load from the rest of the body, is transmitted, so that FSE is going to be equivalent to the F. Okay, so to sum up, the muscle model, Hill's model, represent that the force components are contractile element, parallel element, and serial element, and that will generate the muscle dynamics actually, right? So those muscle length has its own dynamics as a function of those 3 forces. And again, those 3 forces have a derivative of L and L dot, like a force length relationship. So what that means is your muscle length itself has its own dynamics, right? So due to the muscle length, muscle has inertia, so as a length changes, it's going to be a function of its state variable's derivative, L of M and L of M dot. That's how we make a model from the Hill's. That's the Hill's model summary. Okay, so our goal in the beginning is how we can implement the muscle actuation to understand human motion, right? So again, coming back to this simple bipedal walking model, we assume that that's passive walking, mostly actuated by the gravity, but again, it's actually generated by the muscle forces. So if we are assuming the force is applied for the stance leg and swing leg of the muscle, we should do the muscle force implementation. And as again, muscle forces are a function of muscle length and each time rate and activation level and the other parallel or series elements. And again, those L and L dot is now has its own dynamics, right? So we should also solve the muscle length dynamics and solve what's going to be the L and L dot and implement it to finding the F's and use those force to generate the stance leg and swing leg behavior. That's the big picture. That's the outlines, right? So when you want to implement the muscle model using Hill's model, you should add a new state variable here. Oops. State variable of the muscle length and velocity. Like the augmented state variable is not only including your joint kinematics, it should also include the muscle length changes because it has its own dynamics. So for equations of motion, you will have augmented state vector. Time derivative is going to be the state dynamics and the actuation. So state dynamics A is composed by the body dynamics and the muscle dynamics. Okay? And the external input here will be the activation from your nerve, from your brain, right? And if there's any external forces applied to your body, that's going to be also external force components here. Okay, sometimes maybe, I mean, when you have a muscle contraction, length changes that will generate the joint construction configuration changes that will generate the joint angle changes. So maybe your joint angles could be formulated as a muscle length, not directly. I mean, it's very complicated, like parallel and serial summation. So there should be a relationship, but it's not always easy. But if you could simplify them, there are relationship between the L muscle length changes and joint angle. Then you don't have to include those parameters because it's gonna be a function of the other states. Then you can simplify the model. Or you can actually complicate the model by adding another dynamics for the activation. Like instead of having 0 on one, like a state, constant value for the A activation level, you may say that maybe there is an activation signals coming in to the from the brain. There's gonna be a time delay for the A, then you can add another dynamics for the A. So either you can simplify the model, you can make it more detailed and more accurate to represent the behavior what you are really interested in. In that concept, I'm gonna briefly introduce the Huxley model. The Huxley model is also include the dynamics of the filament, cross bridges to the model, the force formulation, because force formulations are based on the cross bridge activation, cross bridge cycling. So if there is a dynamics occurs for the cross bridge actuation or activation, that should be included for the force formula. Yeah, that makes sense, right? So he defines the distribution function that describes the attached cross bridge distribution in terms of statistic manner. Okay, so for the distribution function profile has its dynamics as a function of activation function, and it's not only a constant, it also has a function for the probability of attachment and probability for the detachment. Okay, so for those probability and the distribution functions are formulating the time varying dynamics, and that should be included to generate more in details about how real muscle generate the forces. Okay, so there are also a function of overlap factors of the cross bridges. So by introducing those dynamics for the cross bridge attachment, you should change that will affect the sarcomere length, in turn your muscle length, and that will affect the muscle length force relationship and force velocity relationship as well. And also those contribution will affect the stiffness of contractile tissues and total elastic energy, etc. So by implementing Huxley's model to the Hills model, you can make you can describe the muscle behavior more in detail. And again, it's totally depending on what you are interested to examine, and depending on those problem statement, you should choose the appropriate muscle model to support your hypothesis. Next time, we are going to study how those muscle models are implemented to describe the human motion, like a jumping and throwing.